followed his work. And they were anticipating, because of this wonderful thing he had done with general relativity, this recasting the laws of gravity out of his head, there was the thought he could do it again, and people want to be in on that.
Despite all that he had achieved, Einstein wasn't satisfied.
He immediately set his sights on an even grander goal, the unification of his new picture of gravity with the only other force known at the time, electromagnetism.
Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seemed to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. An electrical pulse sent through a telegraph wire to a magnet thousands of miles away produced the familiar dots and dashes of Morse code that allowed messages to be transmitted across the continent in a fraction of a second. Although the telegraph was a sensation, the fundamental science driving it remained something of a mystery. But to a Scottish scientist named James Clerk Maxwell, the relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related.
When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this
on a compass. Obsessed with this relationship, the Scot was determined to explain the connection between electricity and magnetism in the language of mathematics. Casting new light on the subject, Maxwell devised a set of 4 elegant mathematical equations that unified electricity and magnetism in a single force called electromagnetism. And like Isaac Newton before him, Maxwell's unification took science a step closer to cracking the code of the universe.
That was really the remarkable thing, that these different phenomena were really connected in this way. And it's another example of diverse phenomena coming from a single underlying building block or a single underlying principle.
Imagine that everything that you can think of which has to do with electricity and magnetism can all be written in 4 very simple equations. Isn't that incredible? Isn't that amazing? I call that elegant.
Einstein thought that this was one of the triumphant moments of all of physics and admired Maxwell hugely for what he had done.
About 50 years after Maxwell unified electricity and magnetism, Einstein was confident that if he could unify his new theory of gravity with Maxwell's electromagnetism, he'd be able to formulate a master equation that could describe everything, the entire universe.
Einstein clearly believes that the universe has an overall grand and beautiful pattern to the way that it works. And so to answer the question, why was he looking for the unification? I think the answer is simply that Einstein is one of those physicists who really wants to know the mind of God, which means the entire picture.
Today, this is the goal of string theory: to unify our understanding of everything, from the birth of the universe to the majestic swirl of galaxies, in just one set of principles, one master equation. Newton had unified the heavens and the earth in the theory of gravity. Maxwell had unified electricity and magnetism. Einstein reasoned all that remained to build a theory of everything, a single theory that could encompass all the laws of the universe, was to merge his new picture of gravity with electromagnetism.
He certainly had motivation. Probably one of them might have been aesthetics, or this quest to simplify. Another one might have been just the physical fact that it seems like the speed of gravity is equal to the speed of light. So if they both go at the same speed, then maybe that's an indication of some underlying symmetry.
But as Einstein began trying to unite gravity and electromagnetism, he would find that the difference in strength between these two forces would outweigh their similarities. Let me show you what I mean. We tend to think that gravity is a powerful force. After all, it's the force that right now is anchoring me to this ledge.
But compared to electromagnetism, it's actually terribly feeble. In fact, there's a simple little test to show this. Imagine that I was to leap from this rather tall building. Actually, let's not just imagine it. Let's do it. You'll see what I mean.
Now, of course, I really should have been flattened, but the important question is, what kept me from crashing through the sidewalk and hurtling right down to the center of the earth?